Hi, class, and welcome back. This is your instructor, Dr. Mayas. Today we have a new topic, Chapter 6, Structural Analysis. We have a couple of objectives in this chapter, building on what we learned in the previous chapters. First, we will learn how to determine the force in the members of a truss using the method of joint that we will learn today, and also the method of section, which will be the topic of next lecture. Also, we'll learn how to analyze force acting on a member of a frame and machine composed of pin-connected members. Now, today's lecture discusses the simple truss system, and we'll learn the method of joint, and also we'll learn the zero force members, how to identify the zero force members. And the zero force members means that in some structures, especially in trusses, it's sometimes easy to identify members that does not undergo any tension or compression. So we'll show you how to identify these members and under what condition. We have a couple of activities as usual. We'll go over the application. We'll introduce the method of simple truss, method of joint for zero force members, and then take some problem. All right. On the assumption that you all have read sections 6.1, 6.2, and 6.3. The first reading a quiz is one of the assumptions that you use when analyzing simple truss is that the member are jointed together, and this kind of joint is in fact assumed to be smooth pin joint, meaning there is no friction, and the only forces developed at that pin is only reaction forces up or vertical and also horizontal if we are dealing with the Cartesian coordinate. So the answer is D. Also, when we use the method of joint, typically two equations will be coming out of that: summation of forces in x equal to 0 and summation of forces in y equal to 0. These are the scalar equations that will be necessary for you to apply at every joint in order to solve for the unknown forces. So remember that the method of joints, as we will find later, depends on applying the equilibrium equations in two directions for coplanar structures, and they will provide you with the number of equations necessary to solve for all unknowns. If you look around you, probably especially in at homes structures, you will find structures that look like the ones in the picture. These beams, which are connected together in triangle shapes, are called trusses. And the purpose of these structures, or what we will call it truss geometry, is to take the load coming from the shingles, for example, or the weight above it, and to support the structure from not collapsing. The question becomes what dimension you should choose for these beams, what lengths and what cross-section must be chosen so that they can take all this load. Definitely the first question we should ask ourselves is, how can we identify the force distribution in each of these links? For example, this link undergoing a force, could be a compression or tension, as well as every one of them. And you will see that some of them also might not be really necessary, could be an overkill, but that overkill in most of occasions is done in purpose, so that if there is unexpected loading that structure can take it. Now for this structure, you can see here the normal loading is coming from the weight, right? So someone might think, why need all of these beams if it's only the weight, right? But imagine if there's some wind coming from either direction, or someone is pushing, or there's an earthquake, right? So how can you think of supporting this in a better way, right? So that's why we have sometimes additional beams added. Other challenges that you may look at, especially when the structure is made of expensive materials such as metals or aluminum, it might be, question is, design a truss that can do its job but at a minimum cost, meaning that reduce the number of these beams. So you have to come up with a geometry that can hold the weight or the forces, external forces, yet not many of them. Another common application of using the truss system, which again we said is triangles structures built from what we will call cylinder beams. One of the application is the crane or the frame in the aircraft, right, or space station. Now you might be wondering why these structures are put in trusses. Well, first, you don't want to have a structure that is overweight, so truss can, if it can take the load, then you minimize the number of beams and elements and make it lightweight, right, structures. So trusses is one way to make lightweight structures, which helps, for example, the aircraft to fly, because you don't want to overweight that aircraft. Now I think we are ready to put a definition for the simple truss. A truss is a structure composed of cylinder beams jointed together at their end points using pins. Meaning that, let's take this for example, the truss system is composed of cylinder beams put together, pinned together, right? And this structure have loading coming, which is represented by forces acting on the pins. As you can see here, we haven't added any external load anywhere between the pins, rather than just assume these loads are on the pin. 2D problems that involves structures or beams lies on one plane is called planar truss. A planar truss that begins with a triangle or triangular elements such as ABC and can be expanded by adding two members at a time for each joint, like adding AD and BD, right? It's called a simple truss. So this is a simple truss system. Now the relationship between the number of members and the number of joints in simple truss is simply calculated from this equation, where the number of members, M, equal twice the number of joints minus 3. Let's take an example. How many number of members we have in this? Well, we have 1, 2, 3, 4, 5. Now, does it satisfy the equation? Well, let's calculate the number of joints. 1, 2, 3, 4, right? So we have 2 by 4 minus 3 give you 5. Now, as we mentioned, the analysis of trusses plays an important role in the design. Picking up the right material, picking up the right geometry, cross-section, and also length, and also configuration. Now, this called force analysis, and the force analysis is for a fixed geometry or known geometry, will provide you with the magnitude of tension and compression in each one of these members that constitute the truss. Now there are two assumptions are made. The first assumption made during the design of members and joint of a simple truss is that all loads are applied at the joints. So as you saw previously, we didn't have loads applied along the length of the members, rather than all of them were transferred and as an equivalent force on the joints. Second, we assume that the weight of these truss members are neglected, or even if they are not neglected, then if you're not be able to do the analysis, force analysis, then you have to find the equivalent force and move them to the joint. Second assumption made is that the members are joined together by a smooth pin, and this reminds us from the last lecture that when we have a slender beam with a smooth pin, then the only two forces or reaction forces on this pin are normal to each other, which means in Cartesian coordinate we have x and y. Therefore, the summation of these two forces, or the resultant of these two forces, must be directed along the beam. In the other way, is the beam should have either tension or compression as a result of these two reaction forces on each pin. Now, assuming they have, then the tension which is along the member must be constant at every section. So therefore, the net forces here is the same net forces here, so the tension here is the same as tension here, or the compression here is the same as compression here. Another note is that when we have a compression and a long slender beams, in fact in truss system is a problem, right? And especially long slender beam or thin beam with a cross section, thin cross section, tend to buckle faster. So therefore, when you design or in the force analysis, which you don't care about, the thickness of the beam at that stage of analysis, if the member is undergoing compression, then it's an indication that you should use a thicker cross section to prevent buckling. Well, one of the methods that we'll be using to analyze the forces, tension forces or compression forces on each of these beams is use what we call the method of joints. The method of joints is very simple. First, we assume that each beam is either under compression or tension, and for simplicity, we're always gonna assume that each beam is undergoing a tension, meaning the beams are being pulled, which will exert a reaction force at the joint to oppose that pulling action. So they will be in the reverse direction. So once we establish that, then we apply the equilibrium equations, the scalar equilibrium equation in x and y for each joints. So we apply two equations here, two equations in C, and two equations in A. And this will help us calculate the unknown forces, which are first could be reaction forces at the support or the tension forces. So let's take a look at this problem more details. We want to draw the free body diagram of the truss system that we were looking at in the presentation. So what we have is simply a triangle. It's a pinned here, simply supported, one reaction force, and we have a load. This is A, and this is B and C, right? So the first step is you take each member. So you have A and B, you have C and B, and you have A and C. And we assume that each of these members undergoing tension, right? So this is the tension. We'll give it a name. Let's call it FAB, which is, this is the same FAB. And here we have FCB, right? And here we have also FAC and FAC. Now to continue, we'll take the point B. So we have here a joint. The joint B, we have an external force called here F, and we have also forces coming from the beams equal in magnitude for an opposite in direction. So this is going to be FCB. It's important to follow the same assumption. So we all assume here tension, so the force here equal and opposite, same as in here, equal and opposite, FAB, right? Now for A and C is a little bit different, and in fact we need to make sure that we add also the reaction force. So here we have FAC, and here we have FAB, and also we have two reaction force. I'm going to assume that X and Y positive here, so I'm going to make this as AX, call this is AX, and I'm going to call this AY. These are reaction force coming from this pin, right? We said the pin has two reaction force. And also for C, which is over here, opposite in direction, equal in magnitude, this is going to be FCB, and this is for C here, and for that in here FAC, and because this is a simple reaction or simply supported, it's going to be, I'm going to call it BY. So the number of unknown that we have is 6, as you can see. We have 1, 2, right, 3, 4, 5, and 6, right? So we need 6 equation. So you obtain this 6 equation by applying the equilibrium equation at each node. So apply equilibrium equation at every joint. So you have 2 equations for every joint. So you say at A equal to 0, equal to 0. So you look at A. Where is my A? This is in fact my A here. This is my B, and this is my C, right? And at B, same thing, and 3 at C. So you have 1, 2, 3, 4, 5, 6 to solve the 6 unknowns. That's the method of joints. So these steps can be summarized as follows. First, if the truss support reactions are not given, draw a free body diagram for the entire truss and determine the support reaction. Typically, scalar equations of equilibrium should be used. Second, draw the free body diagram of a joint with 1 or 2 unknowns. We can assume that all the members are in pulling or in tension, and then apply the equation for equilibrium in X and Y. If your result came out as a positive, means your assumption is correct, and that members are under tension. If the force came as negative, then it's under compression, meaning it's opposite to your assumption, so therefore it should be compression. Definitely, sometimes you have to apply the equation of equilibrium to all joints to find the all unknown, or if you're lucky, you can find a point where you can have one unknown to find the result. Now, section 6.3 is in fact give us some shortcuts and some best practice conclusion that we may use during the trust analysis. While we can choose not to do it, but it will make the problem much more lengthy, and you know, you might run out of time. So the purpose of this section is to give you some shortcuts on how to calculate, or how some of the members of a trust have a zero force value, meaning that you don't really need to analyze it. And the zero force value, or they call it zero force members, has certain conditions that we will discuss. Let's first take the following example, or following conclusion that we must memorize and must know how to use it. Now let's take a look at this complicated structure, which is undergoing one load P going downward. Now the zero force members says that one of these, or few of them, might have no forces or no tension or compression if the following is satisfied. If a joint has only two non-collinear members and there is no external forces or load or support reaction at that joint, then those two members are zero. So again, if a joint has only two non-collinear members, let's take a look at this. So the ED and DC are two non-collinear members, right? They are not on the same line, they have an angle. And there is no external load or support reaction at that joint. So what making these two members together is the D joint. So it says if there's no forces at that D joint and they are not collinear, meaning they are not parallel to each other, then these have no tension, no compression, meaning it's useless for this load condition. Similarly, if you look around the same structure, you can identify another two members, FA and BA are jointed at A, and A has no forces, no external reaction, therefore they have no tension or compression, therefore you can drop them. So this entire problem with this type of loading, again, is conditional that you have to look into the loading, can be simplified to that truss, right? So it's sufficient to analyze that to know or to compute the unknowns, and becomes easier, right? Becomes easier. So you reduce significantly the number of work that you should be doing to figure out later that these have zero. Whether you know it or not, you will eventually know that these members have zero. You will find out. It will be verified through your analysis. But again, why would you spend that time figuring this out while we're telling you this is the condition that makes these members to carry zero load. Another case scenario where you can find members with zero forces or without tension or compression is when you have three members from a truss joint for which two of these members are collinear, and there is no external load or reaction at that joint. So let's say another way to say it, if you look at this system, or this truss, and let's take a look at three members that where two of them are collinear. So 1, 2, 3, ED and DC are collinear, and but they're not collinear. They're both collinear, right? And the third member, which is jointed at D, not collinear with them. So would this satisfy? So let's say, okay, so it says then if there's no external load, so meaning D at where they're jointed, there's no external load and it's not a reaction point, which is true for the D, then the third non-collinear members, which is DE, must have a zero force number, or it's a zero force number. So DE can be crossed. We don't need to have it. Now similarly, this condition also apply for the member AC. DC and CB in fact are collinear, and the third member, which is jointed at C, is doesn't have any load at C. CEA is therefore is a zero force number. So in summary, what we're saying that you can drop AD and AC and continue with the analysis of this simple truss. Again, this is assuming that this is the kind of loading we have for the system. Okay, so let's take the following question or problem. So we have a simple truss. This is a simple truss system. It follows the simple truss requirement, where if you start from A, D, B, and then you can continue building the truss by adding two elements at a time with one common joint, which is C. So this is simply a simple truss. Second is this truss is simply supported by a pin at C, so there's two reaction forces at C and one reaction force at A going upward. Great. The first assumption we'll be making is that, before we make an assumption, is we want to find the forces in each member of the trusses. Okay, so it's very important to know what's the problem is asking you before you start working. So it's not asking us anything about the reaction. So there's might not really a need to analyze every member of the structure to calculate all the unknowns, because we know we can calculate. This is a determinant. This system is structurally determinant, simply because we have overall we have two unknowns and one unknown. This is coplanar problem. For this not to rotate and not to translate, it must satisfy the equilibrium equation, and which it does. The second thing is how many unknowns we have, how many support. We have three reaction forces which are sufficient to hold this system stable. So this is structurally determinant, meaning that I can calculate the reaction force here and there, but is it required in this problem? It's not. So let's focus what is needed before you start analysis. All right, so what should you do? That's a question. What's the next step? Well, since we want to calculate the tension or compression at each member, let's say AD, AB member, BC is another member, DB is a member, and DC, right? And there's an external force. So what we need to do is analyze the pins, pin D, right, and A, especially because these two pins will carry these unknowns. But before I do that, is there a way to simplify the problem and make it easier to solve? Well, can we apply this zero force member method and see if any of these members have really zero force before I start analysis? Well, let's take a look. What we have, let's take a look at this. CB and BA are two collinear members which shared a joint at joint B, share another member which is not collinear with them, and that joint B doesn't have any reaction force, it doesn't have any external load, therefore I can drop that. So remember, dB has a 0, so the problem is much easier than it's look, right? So I can do that. And then the next step is to assume, as we mentioned, tension in each one, and then put all the forces on D and A, and then find the unknowns. So I'm not gonna go over the that on paper. I'm just gonna show you these steps, and you can try it at home. So in summary, this is the steps. We'll start with applying or drawing the free body diagram at joint D. So assuming this is in tension, right? Tension, meaning that the force is pulling the AD, therefore D is experiencing some force equal in magnitude, opposite in direction, so it's going down, right? Same thing for DC, right? So it's in that direction. So we know the direction because it's determined by that structure, where the geometry for let's say for 4 give you 45 degrees. So this is 45 degree, this is going to be also 45 degree, right? This is going to be 45 degree. That's why I have here 45 degree. Now once you apply once you draw the free body diagram of joint D, right, you will have two unknowns, and you can apply the equation for equilibrium in X and Y. So let's take a look at X, assuming that the X direction is to the right. This is our X, and this is our Y, right, and positive to the right, and this is positive. Okay, so we have a negative 450 because it's in the left, plus FCD cosine 45 minus, because going back, FAD cosine 45, and must be equilibrium at X, so therefore it's equal to 0, right? Great. So same thing we apply it for the Y direction. So we have nothing coming from the 450, so we have only 2 FAD sine 45, and it's a minus FCD sine 45 equal to 0. Two equation with two unknown. You can, guys, by back substitution, find the values. Now we want to make sure that you understand what the significance of the sign. FCD turns to be has a positive 318 pound, meaning what we assumed for CD is correct. So CD is under tension, because we said this is under tension, we picked. However, AD, although we assumed it's under tension, it's pulling, but it came out that negative value. Negative means your assumption is not correct, only in direction. Fortunately, you don't have to redo the entire problem. It just say, well, it's negative means compression, right? AD is under compression. Now, so what we did so far, we calculated DC and AD. And someone, if we ask, what about BD? We said this is 0. So there's no forces on that. So we need another joint to solve for the unknown. So the simplest joint to find the unknown on AB is to pick joint A, right? So so joint A has a reaction force from that support. Don't forget that. Or assume to be positive up. Just assume it that way. Now we know FAD, but we don't know FAB. FAD value is negative 380. I keep it that way. You didn't have to make any changes to the direction. Just keep the same assumption but substitute the exact value you got. So this way you are consistent. It's so simple to make mistakes here. Just, as I mentioned, you assume it here to be intention, let it be intention, right? Don't flip the direction on that. But when you substitute the value with their sign. Now, applying the equation of equilibrium at A in X or in Y, and Y doesn't give you anything regarding the member. It will help you calculate the reaction, which it will, but for the X, it will help you find the reaction force, or I'm sorry, the tension force or compression force on the member. So, as I mentioned earlier, you don't have to solve all the equations. Sometimes you don't need them, because the problem asks you to find the tension only in the members. I don't have to apply the forces in Y, because if I do, so what you will get? You will get AY plus FAD sine 45 equal to 0, and that will give you AY, but I'm not asking you for that. I'm asking you for FAB. So for that you need to apply summation of forces in X equal to 0, which will equal FAB plus cosine 45 multiplied by FAD, and FAD, when I substitute, I must substitute negative, because my assumption here is still tension, and that would give you that FA or FAB is under tension and it's positive. And you can do the same thing for and see, you can calculate FCB by doing the same thing for C. But remember that this has two reaction forces, up and to the right, and you are just required to, or you will be figuring out that you need only apply summation forces in X at FC to calculate the unknown. Okay, so I'm gonna conclude this lecture with this problem. Determine how many zero force member on this structure. We're gonna apply the two methods. First of all, let's look at these three members, 1, 2, and 3. Two of them are collinear. The three of them have a common point or joint A. The third member, which is that member over here, is not collinear. There is no reaction force or external forces at A, therefore this is 0. Just take a look at that two members jointed at the common point, call it C. These two joints at C, which is common, C doesn't have external force and is not reaction. There's no reaction force. Therefore, this and that are 0. Now, if you are wondering what's happening in this side, same case to the left, but except that we have loading at the common point, call it B, right? Therefore, this doesn't qualify to be a zero force member. So the number of members that can be dropped is 3. So this group problem solving, I want you to try it at home. Please, work on it and try see if there's any truss member or any member on this truss system has 0, which apparently none is qualified. So and strategically, when you apply the equation of equilibrium at the joints, make sure that you order it in such a way that get to the point, right, and reduce the number of the unknowns, so that the problem can be solved easily without need of solving many equations. So with that, I will finish this lecture, and I will post homework from chapter 5 for the sections that we missed, and also from this section. Thank you very much.